Format is we're going to try and keep these short and sweet, just 15 minutes, so 12 minutes of talking and a couple questions. So if you have a question, I think it'll go easier if we maybe just hold the questions till the end of the talk, take 2 or 3 questions, and when the questions start, if the next speaker could come up and get their slides up on the screen, that would be great to minimize that context switch overhead. All of the slides should be on the PC here, so I think we should be all set. So again, thank you for coming, and without further ado, we will move on to session 1, software engineering and analysis. And our first speaker will be none other but Mr. Zach Cross. And also after you talk, we'll make sure we play the hand off the microphone game, and so nobody goes and sits, because it's being recorded, so no one goes and sits down and then says, oh my God, that was awful.
Will this clip?
And then just stick that in a pocket.
Okay, cool. Can everybody hear me? Is this actually on?
So it's not, it's amplifying, it's just recording.
Oh, now I understand. Okay.
Please stop the talk loud.
Unfortunately. Right. So let's see. Okay. Hi. So again, for those who don't know me, I'm Zach Cross, and thanks for coming today. I'll be presenting my thesis work on what I've titled Open Source Design versus Proprietary Solutions in an Ad Hoc System, which is a mouthful. So at the most general level, what I did was identify an organization that fit a certain class I wanted to be able to generalize about later, who needed help with a technical project they're working on. I proposed a solution in concept. I actually implemented a proof of concept. And then in sort of a consulting relationship with them, I demonstrated the lessons I learned from the work I did, as well as maybe direction for future work with regards to this project they're working on. And as part of this thesis, on the more rumination side, I generalized this case to a class of institutions and a class of problems. Specifically, this is with the School of Government here at UNC. They have a group called the Environmental Finance Center. Every year they produce batches of reports for utility managers, visualizing rates data, and all sorts of huge data that they don't own regarding utilities in North Carolina, and they're beginning to scale to multiple states. So that's where this gets interesting. And on the right, you'll see their existing solution, which we'll also look at more closely. Now, before I continue, why this client? They characterize arguably a broad class of institutions. They're public. They don't have, or they're likely to never have, technical expertise on staff. And they're public, so think of the university context. Also, they exist with the sole purpose of disseminating knowledge, which is a good thing. TM. Why open source? I don't think I need to tell a room of computer scientists why open source is good. But for the sake of the argument, they're spending a lot of money on what they're doing. Open source is free for the most part. Well, open source is by definition free. There's a vast ecosystem of mature libraries. There's greater maintenance, higher quality software, lower rate of bugs, and all these positives that we know about. Furthermore, they're very dependent on a particular contracting agency and a particular business-to-business technology for their solution, called Excelsius, which you'll see shortly. Basically, it produces a Flash document based on an Excel spreadsheet input, and I don't have to tell you guys that that's bad for something to visualize data. So their existing solution is basically a long-winded transformation of data that starts with reports coming from the utilities, that's manipulated by hand at the EFC, inserted in some database, from which they generate Excel spreadsheets, which are fed into this business-to-business software, which produces a Flash document to visualize this. And they're paying a lot of money for this. So yeah, you see the problem. Let's take a look at their actual solution. And most importantly, this is an offline application. In concept, I think we can all see that this should be a web app, and it fits well with that. But their workload is that annually they produce these reports once. And so there's no mechanism for these utility owners to come in and update their data for the sake of maintenance. It's all offline. It comes on once. And that just doesn't make sense with this model. They could do a lot more. So, and that was not right. Let's see. All right, let's take a look. This is their dashboard. There's a few gauges visualizing some ratios that I admittedly do not fully understand, and I'll get to that point of domain knowledge later. But as you can see, the essential function is choosing a type of bill, a usage rate, and then a comparison group for all these utilities across the state. So you get the point. This is OWASA. You can see the common river basin shared with another 104 structures. Now, let's go back. So, okay, let's take a look at my solution. Again, this is a minimal viable product. It is a proof of concept. And I've said open source. I will qualify this. Google Maps is clearly not open source, but for the scope of this project, it's what I chose because it was easiest to work with, and I argue that it could be interchangeable with something like OpenStreetMaps or whatever that technology is called. Basically, I mapped latitude and longitude points at the core of this. So as you can see, it recaptures the functionality of choosing a utility, choosing a comparison group, and usages. And I was able to extend what they've done by adding some geospatial extensions, enabling searches like this. And this is running on my laptop, so it's not that great. But so I argue this captures the essence of what they did. And again, I didn't include these tabs of auxiliary information because this is not in the scope of my work. So to get into the specifics about what technologies I used to produce that, I used the Python-based model view controller web framework called Django, Postgres, a relational database with geospatial extensions for basically just those radius-based searches. I used Python to do a lot of the brute work that they were doing by hand to sort of knead this data into something I could use in my framework. Google Maps, as mentioned, is not open source, but that's what I use for the location visualization. I use D3 for the gauges, and then some sprinkling of HTML and JavaScript on the front end. The caveat is I could not recreate the entire pipeline. And again, this pipeline I'm describing is that process of taking the data from the utility owners and transforming it to fit some templates to get into the Access database, to generate the spreadsheet for Excelsius, to generate a Flash document. My proposed replacement in concept was to basically introspect that Access database programmatically, and maybe with some manual tweaking on the other side of that, but to create models in this MVC app. And then follow the typical web app paradigm of just using those models to generate views and to interact within the controllers for everything relating to logic. The challenges were chiefly related to the data set. My domain knowledge was not there. I don't know anything about finance or utilities or these rates or even an extensive amount of information about their process because they abstracted a lot of that away from me. They gave me this data set that, in fact, they had worked with for other steps before they handed it to me. So the data I consider the first starting point of this pipeline was actually the result of some other work on their part. But again, for the scope of this project, I limited it to a certain subset of the pipeline. Now, I overcame the biggest problem of modeling that massive Access database using an open source tool called MDB Tools, which it exists just to liberate data from Access databases, which was a really nice find. And with that, I was able to recreate the schema of the database one-to-one, including relationships and constraints and things like that. But and also parts of the data, I could recreate certain tables from the Access database. The problem was that this MDB Tools software generated SQL schema from the Access database, but there was not a one-to-one mapping. And most importantly, I talked about the way they generated those inputs to Excelsius from queries in Access, and those are called saved queries. Those were massive, tens of lines long queries with a lot of logic, and some of them included the results of other saved queries. So naturally, it was exceedingly complex, and for the sake of the project and what I want to do with it, I decided to move on. So yeah, my solution was to automate the model generation based on the Access database to fit into an MVC app. That included some hacks, and after a while I decided that there were too many hacks and I needed to change direction. So I backed off and reframed this as demonstrating what's possible. So for that reason, I used the actual inputs they used for Excelsius at the end of their little pipeline. So essentially sidestepping that last transform that I failed to recreate. So the conclusions of this are pretty broad. And my point was trying to look beyond the EFC as a particular institution, and this is a particular project. And the greatest problem, again, was my lack of domain knowledge. It was a huge bottleneck in this process. And even though I did have FaceTime with them and I had a consulting relationship, they were also very busy. So it was difficult to figure out a lot of the minutiae in this project. Now, I mentioned that they want to scale to multiple states. And that is incredibly hard when you have the kind of overhead they do. They do this all offline annually. And they want to scale. They're currently in North Carolina and Georgia. And they want to scale this to dozens of states. So I envision the replacement to be something a little more generic, as we expect in computer science. Something generic that could fit across states, maybe with some extensions to enable the capturing of variations in data, where maybe a utility is represented differently in some other state. And on maintenance, I believe that this allows for the application to be online, and I envision the utility owners logging into a panel where they have the access rights to modify this data, and then rather than having this annual workflow, which is this sort of batch process, you have a living, dynamic web application that changes as the data changes. And I think that fits well with their whole purpose of transparency, because again, this is all to help the utility owners manage their rates. And again, I argue that my proof of concept shows that this is feasible, especially if you consider my limited knowledge and my limited time frame. I think the EFC is representative of an entire class of institutions, groups that are public, working with transparent, public-facing data, so there's not concerns about confidentiality and things like that, and they can rely on the maturity of the open source community and building a lot of the essential building blocks of the application. And furthermore, the entire point is that they decouple themselves from these institutions that they spend tons of money with in these contracts by using this open source software and by being able to interchange parts as they need to. So, and I also think that an opportunity might exist for collaboration amongst these sorts of institutions, so they could divide their resources instead of spending this all multiple times, reinventing the wheel. So this is certainly the sort of project, a big data visualization project with minimal privacy and security concerns that could probably span across multiple university projects, especially people interested in GIS stuff, like this incorporates. And that would result in higher quality software with a longer lifetime at significantly lower costs. And I reiterate, they were spending a ton of money on this old project. So, questions?
Question two for Zach, while Ian maybe comes up and gets ready.
When you say expensive, how expensive are we talking? If you don't mind sharing.
I'm not sure if I'm able to share specifically, even though they're public and transparent. Let's just say you'd be shocked. Is that fair, Dr. Mansell?
Well, can you give them an order of magnitude?
Yeah, that's what I was going to ask
On the
for.
order of tens of thousands.
Oh,
a year.
geez. That's pretty terrifying.
Yeah. All right. Which I would have gladly taken. Any other questions?
Is this yours?
Okay. Next up, we have Ian Kim and another database-oriented talk.
So there is something I want to project on this projector over here. So this is the old system, and I'll come back to it, but I just want to show that it's really slow. And that's all we really need to do for now. So I'm just going to do a quick search for aspirin, and we're just going to let it spin, because it's really going to take that long. I think I cleared the cache. All right. How do I switch this over to the slides? Is there a... Just here and then... Oh, okay. Gotcha. All right, so I'm Ian Kim, and I work with Professor Diane Pazewski, and we were doing stuff on not only SQL databases and a case study in which we employed one. So before we talk about not only SQL, I have to talk about relational databases. And if you've ever worked with Oracle or MySQL, then you know what this is because you've worked with it. Basically, the idea is that records of data are grouped into tables, which we call relations, and these tables have structure defined over the table columns. So here, for example, under the person table, we have an ID and a name. Intermediary tables, like the person-employer table you see here, those are responsible for linking data in one table to another. And the process of doing that is called a join. So here in this example, we are looking at this person named Jane Doe, and we want to see who employs her. So we look at the ID in person, connect it to the person-employer table, get that ID, and then connect it to the employer table, and we find it's Google. So this is the model of data that we use for about the last 40 years, and it's been a mainstay. So see, we've run here. So you might ask, what is NSQL? It's a term that encompasses a family of databases. So it's not any one particular data model, but what they have in common is that they're all alternatives to the relational data model that we had before. It's mostly just a response to the changing nature of data that we have today. So if you think about applications like Facebook and Google, it's much more connected, and the big buzzword for this right now is called big data. And it has two parts. One is the velocity of the data, which is the speed at which the structure of the data changes. And the other one is volume, which is how densely connected the data is and how big it is. There are different types of NSQL databases, like column-based key value stores and graphs. But today I want to focus on graph databases because that's what we end up using for chemotext over here, which is the case study. So then, of course, you might ask, what is a graph database? So if you guys remember directed graphs in math class, and this is exactly the same thing, so instead of having records in a table, we're going to make nodes in a graph. And these have properties. So you can see we have a name and age property here. Instead of having join tables to connect data in one table to another, we're going to have edges in the graph, and we're going to label them with the kind of relationship that they model. So here, for example, we have these people here. They're all nodes. They have properties indicating what kind of person they are. And we see there's various kinds of relationships here, like you have one direction relationships like father and daughter. And we have a few that are symmetric, like friendships and siblings. And so if we look at going from a relational model to a graph-based model, we see that taking these stacks of records, we break them apart into separate nodes on the right. And starting from one place in the person table, we can see that those links that we had implicitly in the person-employer table are made into actual edges in the graph. And that's how we have links in graph-based databases. And something else that's worth noting is that all of those nodes have equal status, because you notice that in the relational model, a column in one table is not the same thing as a column in another table. In a graph database, they're all just nodes, and properties are what distinguish the types of nodes you have. And of course, now you might ask, why use not only SQL databases? One really big reason is just the size of the data can be a problem. Joins, the process of connecting data, those scale multiplicatively. So if you get really large data, it's going to get painful pretty fast. And the other thing is, if the structure of your data changes a lot, when you create a new column in a table, you have to apply that change to every row in that table. In a graph database, all you have to do is change the properties of one given node, and you don't have to propagate that change to every other node. And there are just some data applications for which not only SQL data models just sort of work better. So if you imagine a database where you're storing like demographic information, then it doesn't really make sense to use not only SQL database as much, because you can just use a relational database and you'll be fine. But if you imagine another data usage scenario like a social network or something, and you're asking questions like, how am I related to this person? Through what people am I related? What kinds of relationships do I have with them? How far away are they from me? All those questions are really hard to answer in a relational database, so it makes more sense to try something else. So our case study was this application called chemotext, which you see over here. It's a database that connects medical citations, chemicals, proteins, and diseases. The foundation of this application is Swanson's ABC model, and essentially this is just the transitive property. If A is related to B and B is related to C, then you can say that A is related to C. So if we have this article B, and it mentions both A and C, then we can say that A and C are related through this article. And the data source of this is PubMed. It's really, really big. It's got over 20 million citations going as far back as 1800. And each citation in PubMed has a number of annotations that show what chemicals, diseases, and proteins are mentioned in that article. So our current setup for chemotext uses this backend, which is a relational model. Basically, what we have to do is that we start in this chemicals database, if we're linking aspirin and headache here. We look at chemicals, we find in this chemical database, we find its ID, join it onto this table, find all the articles that mention the ID, do it again for diseases, and do it again to find what disease that is. So you can see that I put the relative sizes of the databases here next to the labels, and you can see that those chemical and disease databases aren't that big, or tables aren't that big. But if you go to those intermediary tables, they can be as large as 10 million records. So it's going to get pretty big. So some of the problems we have with this model was that the size of the tables was making those joins really, really slow. And considering that if you look at the interface over here, we're supposed to be able to just click through these links here. Like these are all just links that we can use to search the database. That should be fluid for us, but it was taking like several minutes to finish. So we have serious what they call join pain. Just to get from chemicals to proteins, we had to join 2 join tables and 5 tables total. So as a result of this, it's really slow, so slow that it took up to 15 minutes for a query, and for a long time, we thought it just was broken. We didn't even know that it worked because it took so long. And sort of the side effect of this is that those queries can get really complex and difficult to understand just because there's so many joins involved. So on this next slide, I have a comparison of the new system and the old system. And on the left here is the SQL that we're familiar with, and on the right is what's called CQL, Cipher Query Language, and that's what the graph database I use, Neo4j, uses to query the database. So if we look at this here, you can see that this highlighted section is where we're joining the data together. On the left, you can see that that requires 3 different joins. On the right, the single match statement with those arrows does all of that for us. So you can see that this is much more straightforward to understand. It's just all the articles that point to this chemical, show me what other things they point to. And now what I want to do is I have a live demo ready. I just want to show you sort of the data visualization we can get in Neo4j, and also the head-to-head performance comparison. So you saw this running before. It finished on a number of minutes in. And we can see that it's going to take a lot less time here. So let's go ahead and do that. Do you have a browser? So just to explain what this does, you can see that it's basically going through the database, finds aspirin, looks at all the diseases that are connected to it, and it returns a count of articles that it found. So the idea is that if aspirin is co-annotated with something very frequently, then maybe there's a link between them. And the person who pioneered this model, his name was Don Swanson, and he found some links between magnesium and migraine headache that weren't previously understood. So if you look at the data browser, let's see. So we can query for a particular chemical, and I just want to show off the link between aspirin and other things today. So let's try that. All right, so we found this node. And then you can switch. You can see that it has some number of properties, like it's a type, it's a chemical, it has this ID. We can go to this view. All right, so we can see that this is kind of small, but there's 886 nodes that point to this, which is aspirin. So we can expand this, and these are all the articles I mentioned aspirin. So I'm not going to choose all these, because that's going to crash the browser, but let's just choose 5. And now you see that these other IDs link to this. So we can click on this, and we can see what other things mention this as well. And you can see that the very connected nature of this database means that a graph database works really well to model these connections. So you can see that there's already these 6 mentions links from these articles into this. And you can say that this right here, aspirin, is related to these other nodes through articles. And now what I want to do is show you the exact same data usage scenario we're using over here in this database. So if we just copy this query in, replace this with aspirin, and just let it go. And you can see it's almost instant. And if you compare the results, these are for proteins, and you can see that we have this prostaglandin, and you can see that's the same number up there on the right on the screen. And you can do the exact same thing for the disease and conditions, and that's going to be just as fast. Do that, change the name. And there we go. And you can see that should be MI as the first one with 100 something. Yeah, so we have MI up here with 111, and we can see that's the exact same thing we have here. So you can see that that was a pretty dramatic improvement, because this is almost instantaneous versus that, which took several minutes. So there's definitely a lot of advantages to this model, because it just fits the data so well, and that's the reason why the performance difference is so great. So at this point, I'd like to open up the audience for questions, and yeah, go ahead.
Okay, so I'm vaguely familiar with SQL.
Okay.
Can you differentiate between what made you choose a graph
Yeah, so there wasn't. I didn't look too much into other kinds of other kinds of not only SQL databases, and it just felt that Dan and I agreed that the graph seemed to be a very natural fit for this data, and we found that with the performance gains we got, it seemed like it was a worthwhile choice, so we went with it.
And some SQL guy's going to say, I could write the query that would produce that result in a tenth of your data.
It's true.
I mean, that's the thing that always worries me about SQL, is there's some SQL guy who knows what to do. Did you write these queries or somebody else?
I wrote them personally. Oh, you mean these?
Yes.
We have Nick and Sam here.
We didn't write the query.
But like Nancy wrote them for you, right? Nancy wrote them for you, right? And she has very limited data experience. So.
Okay.
Yeah.
Okay. So some SQL guy would say, you just did it wrong.
It was funny because this is actually a subset of the data on both ones. These are both data from 2000 only, instead of the whole, size of the PubMed data, which is like several millions of records. And I forgot to put indices on the first batch of tables, and that was not good. I came back an hour later and wondered why it didn't work. But.
One more question?
So maybe Diane can answer this question better than you can. Is graph database a new name for the network databases that relational databases replaced?
I don't. My knowledge doesn't go that far back, so.
I mean, that was a historical question because the history is that Kahn wrote this paper sometime in the 70s.
Right.
There used to be network databases, and he said, all these links are bad, so you want this joint capability, which is indirection.
Right.
That's stuff there. And then in 80s, object-oriented databases came around, and they said, let's go to again network databases with types. And guess what? I mean, all the manufacturers decided that was still not getting the performance. Or the joint cost wasn't as substantial. So I'm wondering if this graph database is a new name for one of those two things, or?
Perhaps it is. My knowledge doesn't go far back enough to really have experience with network-based databases, but.
But Pursuin is old enough.
I read my history.
Part of the answer is this notion that there's one database type that works for everything is probably wrong.
You can discuss it in the break. Well, thank you, Ian.
Thank you.
Okay, so next we have some more analysis. So we'll have Alex talk about some work in real-time scheduling.
Oh, no. Sorry. My goodness, I missed that. Sorry. So, hi, I'm Alex. I worked this semester and last semester under the guidance of Dr. Barua, and we worked on offline scheduling of mixed criticality job sets in a real-time system. Mixed criticality job sets essentially are jobs sets which contain jobs of varying importance, and we'll get to that later. But first, real-time scheduling. Real-time scheduling is when you have a set of jobs that are subject to strict deadlines. So they have a release date and a deadline that define a scheduling window, and you have to run the full processing time for that job within the window for each job for your schedule for that job set to be considered correct. Here's an example of one correct real-time job set. You can see that J1, 2, 3, and 4 all finish within their windows. A second job set also finishes within their windows, but you can see that job 2 is split, and that is allowed under certain circumstances. One of those circumstances is, the circumstance is preemption. The processing environment that I considered here involved all of these. One processor, preemption allowed, jobs independent, and we used an offline algorithm. One processor means, you only have one processor, and when you have multi-processors, you can run jobs in parallel, but then you have to deal with the fact that you can't run a job in parallel with itself, because then it would be the same. It would not be the same job. It'd be two jobs by definition. We only considered one processor here. We allowed preemption, which means, as you can see, job 2 is allowed to stop processing. Job 3 can go, and then job 2 can resume later. There are certain environments where you begin a job, and then it has to continue to its full completion before any other job can run. Our jobs here were independent. Independence of jobs means that we don't have to run a certain job before any other jobs can run. When you have that sort of environment, a dependent job system, For instance here, you would have to run job 1 before job 2 could go, and then you'd have to run both 1 and 2 before 3 could. We did not consider this situation. We had independent jobs, meaning that job 1 or job 2 could go either before the other, as long as they both finished within their window. Lastly, our algorithm was an offline algorithm. That means that we began with full knowledge of our job set. There are certain algorithms which handle receiving jobs and receiving knowledge of a job right at its release date. Here we have full knowledge of the job set ahead of time. When you have uniform criticality, so you're only considering jobs of equal importance, there is a known policy which is optimal, and that's earliest deadline first. Simply put, you pick the job that is available, meaning you're in its scheduling window, which has the earliest deadline. So here, you can see that job 1 is the only available job at time 0, so we have to pick it. It is the earliest deadline. You can see also that it runs past the release date for job 2. Job 2 does not preempt because job 2's deadline is later than job 1. However, when we get to this point, both jobs 3 and 5 are released. Job 5 has the earlier deadline, so it runs. Then job 3, and lastly job 2 finishes. Job 4 runs then, and you can see that there is some idle time. That's because no job is available to run. That's allowed in earliest deadline first. It doesn't happen until you have finished all of the jobs. Now let's consider what happens when we say that certain jobs are more important than others. They have high criticality as opposed to low criticality. Here, jobs 1 and 3 are of high criticality. Just by looking at this visualization, we can see that if you move job 5 back, you can keep it within its scheduling window, but still run some of job 3 ahead of time. If we do that, the beginning of our algorithm or the schedule will be the same. Then we have some of job 3. Job 5 finishes right before its deadline. Job 3 finishes, and then job 4 happens. This is essentially a balance between two needs. A deadline need, as illustrated by EDF. You can see that this accomplishes our deadline correctness, but does not necessarily cater to our need to put jobs that are high criticality earlier. And it balances the need for high criticality. You may ask, why didn't we just scoot job 3 up and run job 5 later? You have to always keep in mind that to do so would be to push job 5 out of its scheduling window, making our schedule not deadline correct. This is the basic idea behind my algorithm. I essentially scheduled jobs to run in EDF order, but always check to see if any high job could run so that we would not miss any other deadlines of jobs that would earlier run ahead of this early job. The high job that we use is always the earliest deadline job, high job. To accomplish this, we calculated the constraint for each job so that you can find out exactly how much time you have before every job that would come before it with a higher priority would run. Maybe that was really badly phrased, sorry. I'll show you on the next page, you'll see. The constraint value is you take the job's deadline, and you subtract from it the total remaining processing time of every job which would come before it in an EDF schedule. Here's an example. If we only have 3 jobs, you can see that our current high job, our earliest deadline high job is job 3. We need to calculate constraint values for both 1 and 2. 1, you only have 6 minus 2 because you take the deadline, only subtract the remaining processing time of job 1 because it is the first job. But the constraint value for job 2 involves both the processing time remaining on job 1 and job 2 because they would run job 1 first and then job 2 for EDF. So the smaller of these is the second constraint. That means we can run the third job, the high job, only 2 time quanta before job 2 and job 1 have to run. You see that they tightly meet their deadlines. If job 2 had been the smaller constraint, we would have been running job 3 until job 2 was right at the end of its deadline. Then job 3 finishes. The algorithm that I developed was polynomial. It ran an efficient polynomial time. It also was deadline correct and criticality correct, provably. I don't have the formal proof here because we don't have time, but I will sketch the proof of correctness. We can tell that the algorithm is deadline correct in 2 cases. No high job will ever miss deadline, and no low job will ever miss deadline. High jobs, they're easy to consider because they will never run later than EDF. They run at their own location or earlier if possible. No low job will ever miss deadline because we always check to make sure that running a high job early will not cause a low job to miss deadline. Criticality correctness is more interesting, mostly because we have to first define what criticality correctness means. We chose to define it as an H function, which is a high function, essentially mapping the time quantum of the high jobs you run over time versus time. Criticality correctness means that my algorithm will always generate schedules with a high function that is greater than or equal to any other valid schedule's H function. So for instance, this may be the high function of a different schedule. And you can see that at the end, they do have the same number of high job quant to run. They've run the same jobs. This one might be another valid H function. Again, it is equal to, at many points, my H function. But you will never see a schedule that will have more high job time run earlier than mine, or else it would be deadline. It would miss deadline. The proof for criticality correctness is an argument by induction over time quantum. The algorithm that I have written will generate a schedule that will never run idle when another schedule runs high, because if a job is available to run, it will run instead of running idle. That's sort of by definition of EDF. You'll never schedule a low job when another schedule runs high, because if the other schedule runs high, there must have been an opportunity to run a high job, and if there wasn't an opportunity to run a high job, then they would have, I guess it would have missed deadline. In summary, I wrote an algorithm to schedule mixed criticality job systems. I adapted EDF, which is a known optimal solution for uniform criticality. The algorithm runs in efficient polynomial time, and it is provably deadline and criticality correct. Are there any questions?
Totally nailed the deadline. Questions? So did you guys study optimality for this problem?
Pardon?
Did you study optimality algorithms for this problem? Or are optimal algorithms known?
Well, what do you mean? Did I study it? Sorry. I wrote formal proofs to prove the correctness of my algorithm,
Right.
and I studied EDF sort of to do that.
So if EDF couldn't schedule a set of tasks, is there a better way to do it?
No. Sorry. So, I should have maybe explained that. Optimality in an algorithm means that if a feasible schedule exists, this algorithm will find it. There might be other schedules, but this one will always find a schedule.
Great. Thank you. Good job. So, I'll let you find your own thoughts.
I think I can probably manage that. Cool.
All right, so next we're going to move on to some more performance-oriented talks, and we'll start with Sam Guest and some more chemistry-related applications.
Okay, so my name's Samuel. I worked with Dr. Pazewski these past 2 semesters on improving job management in the ChemBench system. So first, I should introduce what the ChemBench system is. It's a chemoinformatics server, and what this means is that the server computationally predicts the biological activities of a molecule by looking at molecules with known biological activities that have a similar structure. The idea behind this is that molecules with similar structures are going to have similar biological activities. And when I say biological activity, I mean things like how toxic a molecule is or whether it's a good antihistamine. So the ChemBench server was started in 2006. It was somewhat small at the time, but it's grown significantly in feature set and in user base since then. The overall idea is that users have 2 options. They can either create a new model or they can use an existing model to predict biological activities. The server is publicly available, so I'd like to show you guys what it looks like. I'm going to be talking about use cases here. Well, maybe. Maybe. Yes, I want to proceed. Oh gosh, do I want to? We'll actually just use Chrome. Yeah. So this is the ChemBench main page. I'm going to log in so you guys can see what it's like to actually request jobs to run. So the three main portions here are the dataset, modeling, and prediction sections of the site. The dataset page allows users to upload a dataset. But the interesting stuff comes from modeling and predictions. So modeling allows the user to select a dataset to create a model. And so here you can see there's an option to choose a dataset. The user then picks a set of descriptors to model the dataset against. We have different sets of descriptors. They vary in number of descriptors. You can see that this set has 202, but this set has more like 2,500. The choice of descriptor set does affect computation time, but not too much, so we won't play with those settings too much right now. That being said, we do offer 3 different algorithms for running a modeling job, and these different algorithms take a pretty different amount of time. So the first one that we offer is called random forest. And this uses a set of mathematical decision trees to model. It's pretty computationally efficient, but it sometimes doesn't work on data sets. Complicated reasons there for why. But if we look down here, we can see an estimate for how long this modeling job will take. This is 2 minutes. That's not too bad. It's pretty fast. However, as I said, random forest is not the only modeling algorithm we offer. We also offer support vector machines, or SVM. And this splits the data set using a hyperplane. And this is actually computationally pretty expensive. Well, somewhat expensive. We can see down here the default parameters. The job's going to take about 13 minutes to finish. So that's already pretty different from our random forest jobs. SVM actually also goes up in range. If we play with the parameters, we could get it to take somewhere around an hour if we wanted. Lastly, we also offer the k-nearest neighbors, or KNN method, which uses a nearest neighbor approximation algorithm. This is computationally very expensive. If we look down here, this job is going to take about 3 days to finish. We could get it down to a little less than that, but we've also seen KNN jobs that run close to a month. So these modeling jobs have highly variable time spent. We also offer the ability to run predictions. So I'm going to choose a data set here, and I'll show you guys what the prediction page looks like. So submitting a prediction, you can submit a set of predictions to run, or you can actually ask for just one. So I'll show you here. This is running just one prediction. We offer the ability to do this interactively because just a single prediction is usually pretty fast. You can see this one just took a couple seconds. That being said, it's common for users to want more than one prediction. This can quickly add up to a significant amount more time running. So yeah. All right, so that is sort of an intro to how ChemBench works for users. Now, what this means from sort of the software side. When using ChemBench, the jobs submitted are basically a bundle of data and requested computation. This computation can happen in one of 2 locations. It can happen locally on the server, or the server can submit it to one of our cluster computing grids here at UNC, the LSF cluster, to be computed remotely. Each job is independent, so they don't have to wait on other jobs to finish before they run, but sort of. Turnaround can be slow because for multiple reasons, one of which is that these jobs just take a while to compute. But the other reason is that jobs sometimes wait on other jobs to finish because our resources are busy running other jobs. So when looking at improving ChemBench, one of the things we looked at is improving the parallelization. And with parallelization, the idea is that since we have multiple computers, or processors, we can divide code into jobs to be run concurrently. We also have to manage what hardware is going to be running what jobs and at what time and in what order. This helps us use all available hardware efficiently. So ChemBench right now is largely already parallelized in one sense. Jobs are independent, and they're already packaged to run separately from one another and in different locations at the same time. whether it's locally on the server or submitted to the LSF cluster. That being said, the benefits from parallelization don't just come from dividing code into pieces. It requires smart job management as to choosing which jobs are going to run in what order. On top of that, we want to make sure that we use all available hardware to us, not just a subset of it. It does no good, well, it does limited good to parallelize code and run it on 2 processors if you have 8. So I picked 2 features to augment in KemBench to help improve the results of parallelization. I wanted to make our cluster implementation extensible. Right now, our code is hard coding the requests to the LSF cluster. There's no concept that there could be another cluster submitted to, which is fine at the time, but actually right now at UNC we have another cluster computing grid, a Hadoop cluster, that we could be taking advantage of. On top of that, we know that hardware is highly variable. It's likely that in the future LSF could be deprecated, we could get access to a new cluster, and so for these reasons, it would be wise to separate the specific cluster we're using from the idea of submitting something to a remote cluster. Additionally, I also wanted to make job queuing decisions more intelligent. The way we were ordering what jobs are run was not the most efficient, and changing that helps us improve the average time to completion for all jobs. So I'll talk about additional cluster support first. This was somewhat difficult in terms of software engineering. As I said before, KemBench has grown a lot since its inception, and this means that the code was somewhat difficult to read at times. And on top of that, it wasn't designed with this idea that we would have multiple clusters in the first place. This meant a lot of changes in a lot of different places. On top of that, it also never makes any decision about where to submit a job to. It basically divides jobs into 2 categories. Either it can run on the cluster or it can't. And if it can run on the cluster, it goes to the cluster. And if it can't, it stays locally. So to try and fix these things, I read through the code and realized that there's really only 2 portions of the code that require LSF-specific code. And that's a processing thread that submits jobs to run on the server, and a job queue that just maintains a knowledge of what jobs are running on the cluster as well as what jobs should be sent to it. And the reason for that is both of those things need to contact the LSF cluster. They need to know how to contact it specifically and how to parse its response. Those things are specific to an LSF cluster. So to change it, I wrote a Java interface that I thought all remote clusters should be able to guarantee. This is a set of methods that can return something like a list of jobs that are currently running on the cluster, or whether a cluster has free slots. Then I changed the code so that our LSF implementations, our LSF code, was all an implementation of that interface. And then I just changed any reference to LSF to referencing the generic interface. And this means that any class that implements the interface can fulfill those conditions. Now, adding a new cluster is just making a class that implements both the remote processing thread and the remote job queue. And I actually have some placeholders there for Hadoop. It's not working yet, but that's because we haven't got the Hadoop implementation specific details. As far as the software engineering goes, it does in fact maintain a list of all available clusters, and it does search through each cluster and tries to find the best one to run jobs on at any time. So now to talk about job queuing. The current implementation for the job queue, it was using a first come, first served model. And what this means is that jobs are run in the order that they were submitted. First come, first served is generally pretty inefficient, although it's not necessarily terrible if job lengths are small or similar. That being said, the job lengths on KemBench are highly variable. They can be a few seconds, like the interactive predictions, or they can take many days. A better algorithm would guarantee that shorter jobs don't spend a lot of time waiting for a really long job to finish before they can run. So to fix this, I implemented the shortest job first algorithm. Now it's worth pointing out that I chose this algorithm based on the set of conditions for KemBench. Unlike with what Alex was doing, I don't have a set of real-time constraints. Preemption is not really something that we had access to on the cluster, and it wasn't as easy to deal with on the local server, or even as relevant. So shortest job first ended up being the most appropriate choice here. And what this does is it organizes the queues by expected job computation time, which, as you guys saw, we have access to when a job is submitted. And it organizes the queue based on how long a job will take. Shorter jobs get higher priority than longer jobs. This results in an optimal average time to completion. Now, again, it's worth reiterating here, this does not change how long a job will run. That is fixed. What we can change is how long it spends waiting before it runs. And this should theoretically optimize the amount of time, on average, a job waits. Additionally, I also made sure the job queues make intelligent decisions about run location. They're going to run on, if it's a remote job, it'll run on the queue with the smallest expected wait time. It won't submit it to something that's going to take forever when there's a free available cluster. So I took the server code and put it on my local computer, and I ran a set of simulations to show what happens with the difference between the two algorithms. This is the result of submitting jobs with first come, first served. I submitted a set of jobs ranging from 60 seconds to 1 second in reverse order of time expected to take. So 60 seconds was submitted first and then on down. Because this was first come, first served, the 60-second job was chosen first and then the 30-second job and so forth. And what this means is that the average time to completion was very high. It was 96.3 seconds. And intuitively, this makes sense. The jobs after the first job all had to wait the 60 seconds for the first job to finish. The jobs after the 30-second job had to wait the 60 seconds that the 30-second job had waited to run, plus the 30 seconds that the 30-second job had to run. So all of the jobs past job number 2 had already waited 91 seconds. This is going to drive our average up. But when we switched to shortest job first, I was able to add all of these jobs before any processing thread picked up a job to run. So what this means is that the queue was organized itself once I added the jobs so that the 60-second job was last and the 1-second job was put first. The 1-second job ran relatively quickly and the next shortest was chosen. This means that actually if you look here, our completion time dropped for every job except for the first job. And this clearly dropped our average drastically. We're at 33 seconds, where before we were at 96. That's almost a third. Now, this is somewhat of a naive algorithm as it is. It's possible that jobs could get starved. If a user submitted an hour-long job, but then after that, a whole bunch of other users kept adding minute-long jobs, the minute-long jobs would be continued to be chosen at the expense of the hour-long job ever running. It could languish in the queue and just never be run. There are a number of ways to fix this, but the easiest way is to just, upon comparing jobs, to make sure that, to examine whether a job is starving or not. I chose to say that starvation was when a job had been waiting for twice its expected runtime length. And when comparing the jobs, automatically gave a starving job higher priority than a non-starving job. Otherwise, if both are starving, then I organize them by shortest job first. It's worth, again, this solution is somewhat arbitrary. Starvation can be defined many ways. When we put this on the server, we will examine sort of experimentally what ends up working best for preventing starving jobs. But just as an example of what, to demonstrate that my algorithm does account for starvation, I have a set of data here. So I submitted 2 jobs right at the beginning of the start of the simulation. Those jobs were 5 and 6 second lengths. The queue automatically organized itself so that 5 seconds was picked first. But while the 5-second job was running, I submitted 2 more 5-second jobs. So what this means is that after job 1, job ID 1 finished, job ID 3 was picked next. Because even though there was a 6-second job in the queue, but there was a shorter job, a 5-second job. However, after job ID 3 was finished running, job ID 2, the 6-second one, had been waiting for about 12 seconds. This is because there's about a second of pre- and post-processing when a job is finished. And that means it qualified for starvation. So even though there was another shorter job in the queue, the 6-second job was chosen because it was starving, or in this case, met the condition for starving. And also, just at the end, I added in a 7- and 5-second job, and they were properly chosen in order of shortest job first. I just did this to show that my condition for starvation was not somehow messing up my shortest job first algorithm. So just a summary for the queuing effects. The idea behind this was that with parallelization, we have the ability to run n tasks at once independently. But if we don't have a smart choice of which tasks we're running, we can actually reduce efficiency gains. Everything I demoed previously was with one thread on my local machine, but the gains are still seen when you have 9 processing threads choosing 9 jobs. You just need 9 times the jobs to see that same effect. And I was going to have a set of data, like a set of jobs of the same length from ChemBench, but unfortunately, it turns out that it's really hard to run a week and a half's worth of simulation overnight because these jobs take a long time. So I'm sorry about that. But yeah. So that's my presentation. Are there any questions?
So did you think up the solution for dealing with starvation on your own, or did you go do a little research?
This was just one that I arbitrarily picked. It seemed to work. But with the way I implemented it, it's just a change in the one Java comparative class. So if we decided that if it stopped working and we need a different method, it's really easy to just change to one class.
Great. All right, and now we're going to have a follow-on talk also on ChemBench by Nick Bartlett.
Okay. Hi, I'm Nick Bartlett. I did my honors thesis with Dr. Przewski over the past year on parallelization with ChemBench. Sounds a lot like what Sam was just doing, right? Basically, what he looked at was how to do job management and how to send multiple jobs to different machines very effectively. I look more at once these jobs have been chosen to be sent to a machine, how to run these jobs the most efficiently on that machine. So whereas he was looking at the making the time that each job waits less, I'm looking at making the time that each job executes less. Okay, so parallelization. Most of you are, well, you guys are pretty advanced, a lot of you, but in general, code is linearly executed. So if you have 3 instructions calculating cosine 789, you'll calculate the first instruction, and then you'll calculate, once that's finished, you'll calculate the second instruction, and so on and so forth. However, with multiple processors, you can run these instructions in parallel on different processors at the exact same moment in time. For example, on the right here, we'll calculate cosine of 7, 8, and 9 at the same time on different processors, and then we can calculate the product once those have returned. This is the idea difference between sequential and simultaneous execution. On the left, A, B, and C each take a time unit to complete, and then you have to calculate the product in another time unit. On the right, A, B, and C each together only take 1 time unit to complete. So then you calculate the product. So the right takes only about 2 time units, the left takes 4. There are a couple problems that arise with this kind of thing. For example, returning the product, you can't run this at the same time you're calculating what B is, because you actually need to have the result of B to calculate the product. So really only independent instructions can be executed concurrently. So how do we do this in Java? Kind of have to understand the idea of threads. Threads are they're lightweight processes that have a kind of minimal overhead for setting up. Basically, your program, when you start programming, acts as one main thread, and this main thread can create additional threads, and these can be run on different processors. So here's an example of doing this in Java. Pretty simple example. We have a main method, which we will count as our main thread, and it's creating 10 threads and running them. So if this were linear execution, you would expect it to see we're in thread 0, 1, 2, 3, 4 in order. But because there's no temporal guarantee, you're running these concurrently across multiple different processors. You see that thread 1 prints before 0, and then 4, or 3, 2, 4, 8, completely arbitrary. You do see that threads that are started earlier tend to output a little bit earlier than threads that are started later, but it's really hard to guarantee. So the example we just saw was an explicit creation of a thread object in Java. This is a really kind of simplistic method for creating threads.
One of the things about doing this is that the task that you're trying to accomplish, for example here, printing out the number of the thread, is tightly associated or tightly coupled with the execution of doing that task. One way to get around this is you can create these runnable objects, which are in essence the task itself, and you can use executors to determine perhaps maybe I want to add multiple tasks to a thread, or you can also make a queue of these tasks and kind of decide when you want to run these threads and add threads to the queue. Let's see. So why do we want it parallelized? You guys kind of got a glimpse of this on the first slide. It can be a lot more efficient. When you are running instructions across multiple different processors, you're increasing the hardware utilization as opposed to running them all on a single processor. And we'll see a little bit of this later when I give you some actual hard data to look at. And some challenges arise. For example, the first example had a lot of subdividable code. You have to be able to split your problem or your task into multiple different pieces that you can run them across different threads on different processors. If you don't do this correctly, you can have really bad performance. It doesn't work out very well. And in addition, some instructions are really hard to parallelize, like the product. You actually have to do that after you've calculated all of those instructions. So in essence, we have to think about not only the machine that you're running the code on, but also the way that your code and program are set up, the semantics of the program. If your program is doing heavy CPU intensive calculations, then splitting the program into multiple threads, in general, if you have multiple processors, will likely increase performance. If you're only doing this on a single processor, then you're not going to see a whole lot of increased performance in general, because in essence, you are running these like sequentially, like we saw on the left piece in the first slide. In fact, it can actually decrease performance because you also have to deal with the overhead of adding these threads and context switching, where you're loading in and out the memory states of these threads. If the program doesn't allow for subdivision, it also makes this really hard to do. So you really have to consider how the program is set up. So when we were trying to figure out where we can apply parallelization in ChemBench to increase performance, we had a couple of questions to ask. We know that we're running jobs across multiple different machines that have different number of processors. We know that we have a lot of different tasks that we can analyze. Some of these are doing computation. Some of these are doing file input output. Some of them are using large amounts of memory. We want to know if we're running this job on an 8-processor machine, what's a good number of threads? If we're running on a 4-processor machine, what's a good number of threads? This can be really hard to analyze because there are so many variables, but you can establish some kind of general guidelines and maybe good practices for what you want to do as far as threading is concerned. So in essence, we're trying to analyze when and where is thread usage appropriate. So one of the samples that we looked at are basically we analyzed a couple of different cases to see when we could do this. And one thing I did was I made a brute force password generation, which basically enumerates all the possibilities of a password given a 5-length input string and all upper and lowercase letters and numbers. So I analyzed running this on, I actually have a machine that work graced me with that has 8 processors, and a machine that I have right now which has 4. So I analyzed it across these 2 different machines running a variable number of threads to look at the CPU utilization and the time to completion of these algorithms. So let's take a look at that. So this first graph is calculating these passwords for a variable number of threads we see on the x-axis, and on the y-axis we see time to completion, which varies from about 7 seconds to 20 seconds. So the brownish gold data is on my work machine, which has 8 processors. It's an i7. It actually has 4 processors, but they're hyper-threaded, so they kind of act as 8 processors. So what we see is that with one thread on the very left, you have 20, the i7 runs in about 20 seconds. You generate, I think this is like a length 5 password with 62 possible characters. So you generate it in about 20 seconds. It's not necessarily the most efficient algorithm. But anyway, then on the 4-processor machine, you generate it in about 17.3 or so. But we see a pretty significant increase in performance when we up the number of threads that we're doing these calculations on. And you actually see that the performance peaks on the 8-processor machine at around 8 or 9 threads, and around 4 threads on the 4-processor machine. And after that, the performance only increases or decreases. So there's a couple reasons for that. The most simple, simplistic reason for it, I guess, is that once you have more than 8 threads, you can't run the 9th thread concurrently at the exact same time on the 8 processors because you have an extra thread. But it is important to note that here we see that for 9 through, I go up to 40 threads here, especially on the 8 processor machine, the performance is still much better, even all the way up to 40 threads than it was with 1 thread. So it seems, what we can kind of get from this is that a lot of times it's actually better to err on the side of more threads than less. Basically, any time that your CPU is idle, it can be, it's a lot worse than having more threads than are necessary. So here's some CPU utilization data. As you can see here, this is the same brute force password. The 3rd processor is basically sitting around doing nothing. The other 3 processors kind of share the workload a little bit, but you have an overall CPU utilization on the machine at about 32%. Whereas if we up calculating the same number of passwords, the same exact thing to 4 threads, then we have a lot higher CPU utilization, and they're basically getting the best performance out of the processors that you can. So I also decided, okay, well, what if we're doing file I/O? Same thing, but the thread is going to write to the file every time we calculate a new password. So we're calculating like something like 9 million passwords or something, and we're writing to a file every time. So the original time to completion is a little bit higher because we're doing a lot of file input-output. But with 1 thread, you see it's about 60 to 70 seconds. And you see an immediate performance decrease when you up it to 2 threads. This is because when you're writing to a file, both threads can't be writing to the file at the same time, assuming you want some form of consistency. So the threads are sitting around idle while they're waiting for access to the file. So 1 thread's writing to a file, the other thread's waiting to be able to write to the file. So when you increase the number of threads that are writing to a file, it can decrease the performance pretty significantly. And it only gets worse as the number of threads go up. The top is the exact same graph you saw in the last one, brute force algorithm, no writing at all. You see CPU utilization is about 100% across all 4 processors. The bottom, you see we're doing file I/O now, and the processor utilization is a lot less, about 67% as opposed to 100%. So what does this mean for performance? In general, performance is pretty highly variable, depends a lot on your code, depends a lot on your machine. Few things that we can kind of take away from this, though. Having idle CPUs is, in general, a little bit more costly, or in some cases, a lot more costly, than having overhead for having too many threads. In addition, synchronizing on any kind of highly contested data structure or doing a lot of file I/O can have significant performance problems if you increase the number of threads. In general, it's best to go ahead and test whatever program that you're running or you're in separate execution environments for a variable number of threads to figure out where the sweet spot is for your program, where it has the best performance. So how did I apply this to ChemBench? So Sam touched on this a little bit or in the last presentation, but ChemBench does this QSAR model generation, where quantitative structure analysis, or structure activity relationship, where basically we have a mathematical function which gives the properties of the molecule or chemical that you're searching and relates it to its biological effect. So in order to do this on our machine, what we do is we have this SDF file, which defines the structure of the chemical or molecule. And for each piece of information in the structure file, we calculate descriptors. So after we do that, we can take the descriptors and do some statistical analysis and kind of get an experimental value. But really what we're looking at for parallelization is this step, from the SDF file to the descriptors, because it's really for each operation, it's a really divisible operation. So for this generation, we utilize the chemistry development kit. One of the things we utilize is the chemistry development kit. It's a jar file. Basically, we hand it an SDF file, and it hands us back descriptors. It's pretty costly. You can calculate up to thousands of descriptors with CDK. Sometimes we only use, it depends on what you want to pass it. You can define how many descriptors you want to use. But it can take large periods of time. When I ran one this morning, it was taking hours, actually. So in general, the example I'm going to show you in a minute took about 110 seconds to run, just stock right on the machine, but I'll show you that later. So what I wanted to do was subdivide this problem of descriptor generation and kind of put it into multiple threads and see if we can run it on processors in parallel to increase performance. There are a couple of different problems. I already mentioned this jar writes to files. We're accessing some external executable jar file and running it. We're doing some really complex CPU-intensive calculations. But we're going to take a look at that. So the approach that I took is that I took the input SDF file. I split it into temporary SDF files and passed them into the jar. Basically, created a new thread for each temporary SDF file and passed these input files into the jar and got temporary output files, these descriptors. And after I did all of that, I then, so that I don't have to have a lock on these writing files. So after I did all that, I combined all these output files and had these list of descriptors. So the same process as before, same output file, we just split it up. So taking a look at the performance, we see that, like I said before, on this, what I did was, much like Sam, I took the ChemBench development environment and put it on my local machine and ran it on 2 local machines, actually. And we see that the performance is about 109 seconds on both of them to start out with. When you increase the number of threads to 2, so you split this SDF file into 2 SDF files and pass these to the executable jar and then et cetera, you see the performance drops to about 70 seconds, which is pretty significant. It's about 30%, a little over 30% increase in performance. But it's kind of not as much as we were expecting. There's a couple of reasons I think that this might be. The primary of which I think is that the jar itself does calculations which are not necessarily related to its input. So there's some amount of startup time for each thread that is running this jar file. And I'm not exactly sure what that is, but that's kind of what I want to look at, some of what I want to look at in the future, which is to look into this, or delve into this jar source, determine what exactly it's doing, see if I can parallelize it anymore, increase the performance of the jar, and et cetera. So CDK is only one of the methods we use for general descriptor generation. There are a lot of others that we can introduce parallelization into, and in addition, the QSAR model generation flow could also use a whole lot of parallelization. So there's a lot of future work in this area.
Questions for Nick while we
Sure.
Just curious, so are the input files not read in the read-only fashion? I just asked because you split
The input file is read in
the
read.
XDF.
Sure.
Are they like modified by the algorithm?
So no, the SDF files are not modified at all. So basically what you do is you have this SDF file, you pass it to the jar and it outputs to an X file. So you can pass any SDF file to this jar file and it will input out these descriptors, or output these descriptors. So we can, the SDF file is kind of defined by us, so we can do whatever we want to do with the SDF file.
Great. And our final talk here is going to be by Mohsen, and this is another parallelization talk using a different programming model and different hardware.
Hey everyone, my name's Mohsen. Today I'll be talking to you about how you can use GPUs to develop an efficient implementation of neural networks. And because this was an interdisciplinary project, I had the good fortune of working under 2 great mentors, Dr. Flavio Froelich from the psychiatry department and Dr. Jan Prince from here in the computer science department. So first I'd just like to give you a little background on the biology. So neurons are the basic processing unit of the nervous system. And the way they work is they're connected to a bunch of other neurons. They fire action potentials, and then those action potentials go on to stimulate those other neurons, their neighbors. And if those neurons are stimulated enough, they also fire action potentials. And so in this way, they process information. And there's a great diversity of neurons, and they can connect in very complex ways. So what I was interested in studying in were large-scale networks. And these are interesting because recent studies have linked particular large-scale network dynamics to specific brain states. And these range from everything from normal states to pathological states. And here's an example of a large-scale network dynamic. This is present in, this is called slow-wave sleep, and it's present in deep sleep. So you see activity begins medially. So you're moving left to right. Activity begins medially, and then it slowly propagates outward, covering the entire cortex. And so this is an example of an interesting dynamic. Although these are very interesting, they're difficult to study using traditional tools used in neuroscience because those tools only allow access to a few specific neurons. But we can get an idea. We can simulate this using models where we have access to data of all neurons. And so here, these are snapshots of the model that we developed. And you can see that you still see the same interesting spatial pattern. But here we have access to all the information for every neuron. So here I'm showing the membrane potential, the rate of fire, and the synaptic depression for every neuron. So although I don't really understand why an engineer would need a reason to make things faster, I guess it's a fair question to ask. For our use case, it was important for us to be able to run lots of experiments. And in particular, what we were studying was a stimulation paradigm called TACS, which is transcranial alternating current stimulation. And we wanted to see if we could modulate the brain. We could modulate the network activity to different states using the stimulation paradigm. And in order to do that, we needed to run a large amount of simulations where we tweaked the stimulation parameters in order to find the stimulation paradigm that's ideal for modulating network activity. So here's an example of where we changed the simulation frequency and the simulation amplitude, and we were able to find an ideal frequency and amplitude to entrain the network. And in this next set of experiments, we looked at diversifying the spatial pattern of stimulation, and we needed to run hundreds of simulations, and then we were able to find which stimulation paradigms were more effective. Another use case is possible integration with live tissues. So you can develop sort of a feedback loop where the live tissue actually talks to the model and stimulates particular neurons. So the model are basically two planes of neurons. There's a plane of excitatory neurons and a plane of inhibitory neurons. And so the excitatory neurons shown in blue, there were 160,000 of those, and they connect to other excitatory neurons in addition to the inhibitory layer, neurons in the inhibitory layer. And there were a total of 40,000 inhibitory neurons, and those were excited by the neurons of the excitatory layer, but only connected back to the excitatory layer and inhibited those neurons. So the model that we used was developed by a mathematician called Dr. Zikovic, and it's essentially two differential equations. To implement this, we basically divided up into 4 separate functions. The first is update conductance. So when a neuron is excited, you have an opening of ion channels, which translates to an increase in conductance for that neuron. And over time, those ion channels close and the conductance decays. So that's what that function is doing. The next function is just solving those differential equations to calculate the membrane potential. After that, once we have the membrane potential, we check if it's reached threshold. And if it has, it fires an action potential. And then we have to go out and update the conductances of all its neighboring neurons. And the last function is just general housekeeping, resetting variables, resetting the neuron variables for that time step, and writing the results out to file. So as it's currently implemented on this, or as it's implemented on the CPU, this takes about 80 milliseconds per time step. Oh, and sorry, I forgot to mention, the time step that we're using for our model is a 1/10 of a millisecond. So that's very slow. That's nowhere close to a 1/10 of a millisecond. So moving over to a GPU, so the neurons in the brain process information concurrently, and so do the neurons in our model. However, on the CPU, this is occurring in a serial fashion that's really slow and inefficient, but the parallel architecture of the GPU is sort of an ideal environment for this sort of simulator. However, there are challenges, and Nicholas addressed those earlier, with concurrency. And the first are race conditions, which is where you're trying to, two concurrent threads are trying to access the same spot in memory and modify it at the same time. And the second is determinism. Since we are using this model to run studies, we need results to be the same between runs. And this can become a problem when you have concurrent processes, and I'll get into detail about that later. And the last is minimizing memory transfers. So now we're moving data between two different components, and that takes a long time. And so we want to try to minimize that. So the first thing we did was go after low-hanging fruit, which are the first two functions. And these are basically just giant for loops that go through every neuron and do the calculations for that neuron. And at this state, the neurons are acting independently. They don't need data from other neurons. So this was very easy to move over to the GPU. We didn't have to worry about race conditions or anything like that. And however, now we do have the concern with the overhead with the data transfer, where you have to move data from the GPU back to the CPU and from the CPU back to the GPU. And that added a little bit of time. Despite that, we were still able to get it down to 14 milliseconds per time step, which was 6 times improvement. So the next function is the checking for spikes. This, we need to be a little careful here because, as I mentioned earlier, when a neuron fires, it goes and updates the conductances for all its neighboring neurons. And a neuron may have two separate neighbors that fire at the same time, so they could both be trying to update the conductance at the same time, and that could cause problems. So you have to be careful there. But that's easily solved using atomic operators. And what atomic operators do is sort of guarantee that the operation will occur serially across all threads. However, what it does not guarantee is the order of the operations, and that'll cause a problem. And so what we were seeing is that we got strange results. So in these two figures, we're describing the percent of the network that was active each time step. And what I mean by active is firing. And so these two networks were started with the same exact starting conditions. However, you can see that the results are different. What's important to note here, though, is that the behavior is the same, that this is still an oscillating network. So after doing a little detective work, we found out that the reason was something we all learn in computer architecture, which is that floating point arithmetic is non-associative. And so basically what's happening is if you look at the arithmetic that's going on down there, when you do floating point arithmetic, you have to align the decimal points. And so where you see the red 1 and 0, those bits are being dropped off from that the lower value as it's being shifted to the common decimal point of the higher value. And so you lose those bits. And so the order of operations can affect basically you have non-associativity because let's say you add two small numbers together first, and the result sort of moves a bit over to a place which won't be dropped off. But if you instead had added the higher, a large number with the small number's bits would be lost. And so a way to fix this is to use fixed point representation of the numbers. However, since we knew there was an upper bound to our total, we could use a fancy floating point arithmetic trick, which is basically adding and subtracting by a specific number, which would sort of align the numbers to a common scheme while still keeping the floating point representation. So the number we chose was 4. And the advantages to this approach is that it's very simple to implement, and it's also guaranteed to be deterministic up to a certain upper bound, which we knew we weren't going to reach. There is a loss of accuracy. However, as I showed before, if the results are if the results are minorly different, the behavior is still maintained in the system, and that's what we're looking for. So we were more concerned with determinism rather than accuracy. And so after implementing this, we got the network down to run 8 milliseconds per time step. So the last step was just moving over the housekeeping function. However, some of the stuff here needed to stay on the CPU, such as writing out the results to a file. So what we decided to do was split up the function, keep some of the stuff on the CPU, and move over stuff like resending the variables over to the GPU. And this way we were able to minimize the amount of data that was transferred. And after doing this, we were able to get it down to 2 milliseconds per time step. And so that's a total of 39 times improvement. So there is additional improvements that can be made. So the memory transfer that is occurring can be done asynchronously. And the way to do that is to create 2 buffers on the GPU. So when a GPU is doing computation during a time step, it writes to one of the buffers. And then when it switches over to the next time step, that buffer, the data in that buffer is being sent over to the GPU while the CPU is writing to the second buffer. And those switch back and forth each time step. Also, another thing we noticed is that there's low occupancy with the functions that are running on the GPU. And basically what that means is that for the amount of time that the kernel is loaded, or the function is loaded onto the GPU, not a lot of the processors aren't active for a lot of the time. And there can be a lot of reasons for this, but what we think it is that there's low computational intensity in the problem, and computational intensity is basically the number of operations you do per memory reference. And so what you want to do is you want to have lots of operations going on and a very small amount of memory references. So what we could do what we could do here is to use a more complicated integrator, which determines the memory potential. And basically what that'll do is allow us to use a larger time step so that we can have, so we're basically using more of that time that so we're basically utilizing that time that's being spent going to get stuff from memory. So this was a cool project, and it's part of a new class of, so GPUs are becoming very common because of the video game industry, and this is a cool application use of those GPUs. And again, we can integrate this with live systems, and this is something that we have in our lab. It's called a multi-electrode array, and so what you can do is place a live slice of brain on here, and it's spiking, and you can measure the spikes and then feed that to the model, and so you have this feedback loop. And also, Obama recently announced a brain mapping project, and they'll definitely have uses for simulators in order to accomplish that. And lastly, I'd like to thank my friends at the Froelich Lab, especially Kristen Sellers, who was an experimental collaborator and helped validate my results in the real world. And also ITS Research Computing and Stephen Groner for initial code development.
One or two questions? Zach?
OpenCL or CUDA?
CUDA.
And you also said the original time step is 1/10 of a millisecond, so you're running it 20 times, or 1/20 real time?
Yes, yeah.
Okay, cool.
Did you consider, instead of the scatter operation where my potential affects my neighbors, trying that to a gather where I look at all my neighbors and put the number here and then there's no contention again?
Yes, we had considered that. However, the solution that we implemented was a lot simpler. And so we went with that one instead.
What you've seen here is actually Math 566. 411 is great. We'll make it that, but you can do Math 566. So thank you. So let's take a break. Hopefully there's some refreshments outside.
All right. Hello, everyone. My name is Dennis Given. I'm a junior here at Carolina. And my research was done in the project Nutrition Nation, which was a project with the Carolina Population Center for monitoring our food environment via crowdsourcing. Before I discuss the project, I'd like to first kind of talk about the motivations of why we even started to do research here. And that is that there are a few good databases containing nutritional information that's accurate and not full of errors. Companies like Glaxo, if any of you are familiar with, say that they have great databases of nutritional information, but they don't have timestamps. There's no geographical information associated with them. And so what many research groups need, and to know what we're eating, we need a good database where we know exactly what kind of nutrients go into the food that we eat every day. So the overall project was, for Nutrition Nation, was to create a system that would streamline the collection of nutrition facts, verify that information, and then store it in a database. And my part of the research was specifically here, where I had to find an accurate and efficient way to extract nutrition facts information from images of nutrition facts panels on the side of boxes, and et cetera, and whether that was feasible. And before we kind of go on to all the components of the process, I'll first discuss optical character recognition, also known as OCR, which many of you are probably familiar with, which inputs an image, tries to identify all the characters in that image, and then outputs a text file that has all the approximate words that it thinks are in the image. And some open source OCR engines are Aspire, Tezrac, which is now being developed by Google. An example of a commercial OCR engine is Abby FineReader, which many of you may be familiar with. And so when I learned of OCR engines and the technology, I just figured I could throw a picture of a nutrition facts label, send it through the OCR engine, and I would just get a text file with all correct information. And as many of you probably know, this failed epically. And I realized that there had to be, I had to wrap this component basically with a pre-processing and a post-processing. And so the overall process looks like this. We take a raw image with a mobile phone, so most mobile phones use JPEG images, and we send it through pre-processing where it goes through a cut, a rotation. Then we take that image, the best quality image we can give it, send it through an OCR engine, which gives us an output file, which is in text format, and then run a post-processing to take that text file, try to identify as much of the information in it as we can, and then output it as a CSV file. So I'll just quickly go over the components. So the pre-processing, the goal is we want to give the OCR engine the best quality image we can so that it can identify as much of the text as it can. So this involves cropping the image. Hopefully we want to give it just the label where the text is and not the box with all the pictures that might confuse it with noise. Next, we also want to rotate it. OCR engines perform best when the text lines are completely horizontal. And as many of you probably know, taking a picture completely vertically on a mobile phone is very difficult. As I mentioned, OCR, I specifically use, or this project used Google's Tezrac OCR engine. It's open source. There's a ton of documentation on it. And it was originally developed by HP for their scanners in the 90s when they were sending documents through. And then the post-processing is required because it's very difficult for an OCR engine to get 100% of the translation correct, as many of you may know. And it needs methods of fixing the errors. So with the Levenstein distance method, approximation methods, and then we also want to output it as a CSV file. It's much easier to grab the information to later store in a database. So I'll discuss, there are two implementations in each of the three components. And I'll just discuss each first, but both implementations of pre-processing use edge detection. And this is because there's so many factors that go into or so many variables considered when you take a picture of a nutrition facts label. Lighting, color, and one thing that stays consistent is the lines, the outline of the label. And so edge detection, as maybe you've probably come across, is just an algorithm that finds pixels in the image that it believes to be an edge, and that's based on gradient, how quickly the color in the image changes, etc. And so that was one of the easiest ways to identify the proper places to make the cut to extract just the label from the raw image. So the first implementation, this is where the two pre-processing implementations split. The first one is this column and row summing. The first step is to fill this matrix of size, width, and then twice the height of the image. The top half is the binarized image with zeros and ones, zeros where there's no edge and then one where there are edges. And the bottom is just that same image flipped, I guess on the long end. And we sum across the rows and columns and find the maximum points. So wherever we believe there is an edge of the label, we expect that the sums, when we sum across the columns and rows, will be at those points. And the reason why we do this flip is through a lot of the work I was doing, I realized that a lot of times edges were lost because the label or the box or label itself was too close to the color of the background where the image was taken. So to kind of guarantee somewhat of a safe cut, we do that flip so there's still some value that crosses that threshold so we can make that cut. And then the rotation method, once we make our first cut, we kind of go from left to right, from top row to bottom row, and we try to identify the x values at which we run into the first edge pixel. So we find basically the slope of the edge, many times is very small, but to be able to determine that and then rotate the cut image by that angle to straighten it out and try to give the OCR engine the best possible horizontal image. As you can imagine, there were some problems with that implementation. Obviously, as I said, it's very difficult to take a picture completely vertically, so the sums were spread out across several columns. Also, with the rotation, sometimes there's noise in the edge-detected image, so pixels that believed to be an edge but wasn't threw off the slope value and therefore threw off the rotation value. So there needed to be a better way, or a different way at least, to try and capture the lines in the image, and I looked to the hue transform, which basically takes an edge-detected image and tries to identify where in that image there are going to be lines, or I guess from the original image where there are lines present. As you can see, the middle one is the edge-detected image with black as non-edge and white as edge pixels. And then the blue lines represent horizontal lines, and then the red lines represent vertical lines that believes to be in the image. Based on these lines, we make a cut at where the horizontal image, we basically identify the top left, top right, bottom left, bottom right corners of the image based on the intersections of those horizontal and vertical lines. And then a new rotation method. So we just want to use what's already given to us or what we've already found, and that is these lines from the hue transform. And so what I calculated basically the average slope, or how far from horizontal the average slope of these horizontal lines were. And then from there determined what the necessary rotation was to get those lines as, at almost completely 180 degrees. And I ran this experiment on I think 25 images and was able to come up with this equation where you just feed it the average slope of the horizontal lines, and it'll just give you exactly how many degrees you need to rotate the image. Next component that I'll discuss briefly is just the OCR engine. In my time of research, they began with version 3.01 and then moved on to version 3.02. So I wanted to use both in my experiment, see how they performed. There are very small differences in terms of accurately identifying words, but there were differences in the orientation of the words. So in 3.01, sometimes it wouldn't translate words as correctly. O's were zeros, L's were ones. But the ordering of the words was always pretty close to what it was in the nutrition facts label. Calories from fat was all in order, all sequentially. But version 3.02 was better identifying words, but then calories from fat could be spread out across several lines of the text file. And so this is just an example of a text file outputted by the OCR engine. It's not great, so obviously you see why we need the post-processing. So the first thing we do, and this is before we split into the two different implementations of post-processing, but we tokenize the text file. So obviously something like total fat would be a nutrient, quantity would be the 2.5, and then the unit would be grams. Just to make things easier, just to identify what's what. And then we have two different methods in the post-processing. The first is nutrition facts panel method, which basically we create a data structure that's almost identical to a nutrition facts label and give it very, very strict parsing rules. So it's filled sequentially as it's going through the text file. And then we have another implementation, NQV, which stands for nutrient quantity value, which is much more loose. It packages nutrients based on it uses the nutrient and then the following quantity and unit, and packages them and then matches them to a predefined list of nutrients. So the experiment that I ran, and the goal of this experiment was to determine, because we now have 8 different systems, 2 implementations in each of the 3 components, we want to determine which of the 8 is best or can translate the information the most correctly. And so this experiment was run on 63 images found on flat matte surfaces, so cereal boxes, granola bar boxes, those take-home dinner trays. And the evaluation of the experiment. So of the 63 images, I filled a CSV file with all the correct information manually to compare to. And each of the 8 different systems would output a CSV file, and we just ran an evaluator that compared the CSV file to the truthful CSV file. And what we were looking for were the 18 total nutrients to check, and 7 of them are we labeled as core because the FDA requires on nutrition facts panelists to have these 7 core nutrients, and you can kind of see servings per container, calories per serving, and ones with all the yes next to them. So the results. We based our success of our system based on, of the 18 nutrients, how many of them were correctly identified in the outputted CSV file, and also of the images that were processed, how many had the core nutrients, how many of the core nutrients were captured. And looking at our results, the heat transform implementation for pre-processing was clearly better. It cut the images properly. It gave OCR the best possible image to process. Now, when it comes to the OCR and post-processing, so the later 2 components, the results are pretty inconclusive. There were 2 main processes. One was using the heat transform version 3.01 of Tesseract and the NFP post-processing method. And the other was the heat transform 3.02 of Tesseract and the NQV post-processing method. And I was trying to decide why those 2 were the best. And as I described before, 3.01 of Tesseract is very sequential, just like it puts everything in correct order that's found in the image. And NFP, with its strict rules, is much more oriented towards that kind of text file that's outputted. Meanwhile, 3.02, although it gets more of the words correctly, is much more freeform. But the NQV post-processing is exactly that, much more freeform, so it can capture a lot of the words that might not be in correct order. So conclusions, future work. Obviously, in my results, I was able to get 80 to 90% accuracy on the 18 nutrients for many of the images that were sent through. But obviously, that's not good enough. You don't want to know only 80 to 90% of the facts of the food you're eating. So possible improvements. One is the ensemble method, which would basically take all 8 of the systems and take all 8 CSV files and have a voting process to determine what exactly it believes that value to be, putting more emphasis on the 2 systems that we believe to be better than the other 6. And I attempted this in April of 2013, so this month, and improved accuracy just a little bit by a couple percentage points. The next thing is to train Tesseract. It has the ability to be trained based on font and dictionaries. And we'd like to, for future work, to work on circular surfaces and labels that are in color and all sorts of color. So that's it. Sorry.
Do you characterize at all the types of errors that you were getting? I mean, the source of the error, as opposed to trying to come up with better engines?
Absolutely. Sometimes it was just that it wasn't in the text file when the OCR engine translated the text. Other times it was just lost. There were random symbols thrown in and the spacing in between. Because, like in a text document, all the text is right next to each other. But in nutrition facts, obviously, they're spread out and it's difficult to associate different words with them, so they'd just be lost.
Yeah, I was going to ask, so the places where you look at the nutrition label, you kind of know what to expect.
Yes.
But the values, you kind of don't.
Right.
It's a very dense coding. So it seems like the error there would be somehow worse.
Right.
So it would give you 9% instead of 1% or something.
Exactly. It was, that was probably the biggest challenge, too, especially with that percent symbol. It was tough to identify.
So let's go through the training.
Absolutely.
So I was going to say, from version 301 of here to 302, the biggest thing you couldn't go to 302 is to take all the 10 and make them one space 0. And that's the thing, 302 kept adding more spaces there with the words, and you couldn't do it.
All right, thank you.
All right, next we have Isabella. Work in Canberra. And first we have to move it all to mine.
So this work is about friend lists. By friend lists, I mean reusable name groups, which allow users to manage their friends into groups and perform groups of specific sharing. And in Google+, these are called Google Circles, and in Facebook, they're called friend lists. One current problem about these groups are that users do not take efforts to create them, but they do want group-specific sharing. So as computer scientists, we want to solve this problem by reducing the efforts and helping users to create this list. One current approach to solve this problem, which was developed by Kelly Bacon, she basically recommends friend lists based on the friends of the user and the connections between the friends. And the algorithm basically identifies cliques in graphs and form these cliques into friend lists. And a clique basically means a group of vertices that are all connected with each other. And in this example, Alice, Bob, and David are all connected with each other. So they form a clique. And that clique then combine with other cliques to form a friend list of Alice. And Kelly then presents the friend list to the user on paper. And the user can mark the paper to add and delete friends. So the focus of my research is to do better evaluation of Kelly's algorithm, and also collect more data for future algorithm. So here's a slide to visualize my contribution. As I said, I collect more data. And I also built 2 integrated Facebook apps to replace the paper evaluation. And my platform allows users to directly reuse the friend list into their Facebook. It is also paperless, so it provides better privacy control. And it also measures users' efforts by evaluating how long it takes for the user to complete on the UI. It is more realistic, and also it provides UI design evaluations and can resolve UI design issues. Here are a list of questions I faced. First, I want to start with what data to be collected and why. First, I decided to collect the friendship start time. This data is very important because we want to look at how users' social graph evolves through times. And this data is collected from retrieving all users' posts on their timeline. And I basically find the posts that say A and B are not friends. So I collect the data with user IDs and the timestamp. Second, I also look at the Facebook groups, which are just groups generated by the user for information sharing within the group. And we think these are important because they may imply user social groups. And the information I collect here include the name, the privacy setting, the description, and the members of the groups. Lastly, I also look at the existing friend list of the user because these are the partial social groups that the user already created. And these information include the name, the type, and the members of the friend list. The next question is how the user interface looks like. First, user will run the friend list recommender on Facebook, and Facebook will ask user to grant permissions. And then the browser will say your data is being collected. And after a few hours, user will get a notification saying their friend lists are ready. And once user click on the notification, he will see the evaluation interface. It has two main sections. So friend list sections basically shows one friend list at a time. And the friends pool section loads all users' friends from Facebook. Once user is done with one list, he can then give a name to the list. He can choose between publishing the list only to the researcher or publishing the list to both the researcher and Facebook. The user can also discard the list so the researcher would know this is not a friend list of the user. User can also navigate among different friend lists, suggested friend lists. And to help user to identify the list, I give each list a name, which is a string constructed by the first member and the last member of the list. To add members and delete members, users can check the friends from the friends pool and as selected and move it to the list on the right. To delete members, user can uncheck the members on friend list and move it to the friends pool. If the user decides to publish it to Facebook, he will then get the same Facebook friend list on his Facebook account with the same members and name he gave on our UI. In the end, user can also create new lists by adding members to it, and so that the researcher would know there's a missing list from the recommendation. Here is the researcher's user interface. Basically, the UI, I keep track of all the user's interactions with the UI, including the time user started on the UI and the list the user worked on, as well as the members the user added and deleted, and the name user gave to the list. So the next question is the implementation of the UI. Basically, all the data collections are done through the Facebook Graph API, which is the primary way to access Facebook's social graph. This is basically HTTP post and GET with access token, which is temporary random string constructed by Facebook to identify user sessions and user permissions. And the Graph API returns data in JSON format. It supports retrieval of nodes, connections, and attributes of Facebook Graph API, of Facebook social graph. And it also has limitations. For example, user can hide themselves completely from the Graph API so that we can't see their data. Secondly, you can't make more than 600 calls per 600 seconds. And also, some attributes are not explicitly supported by the Graph API. I created two apps for the implementation. The first app is a friend list recommender, which is basically a PHP app calling the Java CGI program on the department server. And the Java program will retrieve the user information and recommend a friend list. And the second app is a friend list editor, which is just a client-side HTTP and JavaScript. And on that app, user will be able to see all the recommended lists and make modifications on it. Here are some protocol-level interactions among different processes. First, user will run the friend list recommender on his browser. And then Facebook will load the PHP scripts hosted on the department server. And next, the PHP will ask for access token. And then Facebook will ask for users to grant permissions. And after that's done, Facebook will give PHP the access token, and PHP will execute the Java program. Once Java program is done, the PHP then push the notification, and Facebook push the notification to the user. And once user click the notification, Facebook server then asks user to grant permission for the friend list editor app. And once that's done, Facebook will load the JavaScript program from the department server as well as the recommended list. Then user can edit the list in the browser and submit the finished list to server as well as Facebook. So how the Java CGI program works, it has two main parts, the data collection algorithm and the recommendation algorithm. First, the data collection algorithm makes a series of Facebook Graph API calls to the Facebook server and get the return data in JSON format. And then it parses the data and writes the text files into the department server. The recommendation algorithm also reads text file from the server
and then write the recommendation back to the department server. Using the apps I created, I did a user study with Kelly's algorithm. And this user study had 6 participants. And they're all my Chinese friends in UNC. And here are some results. First, each user on average got 16.7 recommended lists. And among this list, 55% were confirmed and 45% were discarded, which was not as good as Kelly's result. But like, one possible explanation for this is that some of my friends, they're not very active Facebook users. Instead, they use the Chinese Renren, if you have heard of it. But I also found Kelly's algorithm to be very accurate because on average, there's only 0.3 missing list claimed by the user. Also, on each confirmed list, there's only 0.8 and 0.3 added and deleted members, respectively. And from my point of view, the most interesting and most important metric on this table is the total time spent on the UI. On average, users spend 19 minutes, which I think is really good because it showed the usability of the UI. I also got some comments from the participants. Some people said they really like the profile pictures because it really helped them to identify their friends. And some other people said they like the clear illustration of who is on the list and who is not. But one user also said he wanted more friends to show on the table at a time, so he suggested that the picture can be smaller. And another user said he wants more meaningful names to the recommendation list, which means he wants some level of predictions on the list names. Looking forward, the next steps include like using subjects other than my Chinese friends, and you should contact Jacob if you want to volunteer. And analyzing profiles, events, tags, comments into the recommendation, predicting changes in existing friend lists, and also recommending privacy settings for the friend list. And thank you for listening. I want to open up for questions.
Questions? Was the Facebook's API limitation a problem for you to just throttle away processing, or was 600 requests per 600 seconds fine?
Well, like it did cause some problem for the data collection because we need to get the friendship start time, and that's done through the posts. And like Facebook limits your request to the timeline post to like 25 each time. So like if you are really active Facebook users, like you have a lot of posts, and like if you want it, like each request only returns 25 posts, like it's gonna be a problem too. Like it will take a long time to process like all the posts.
So the Facebook feature where you can show a friendship wasn't something accessible via
No,
API?
it's not explicitly supported.
Okay.
Yeah.
Great, thank you. Next, we're going to move on to a more aquatic theme. And Winston is going to talk to us about his work on fishing.
Fishing. No, actually, I don't know how to do that one.
And then just, so your video is there.
Cool. Yeah.
It has the same name, so it should work.
Awesome.
So just click on your tones.
Perfect. Thank you. Cool deal. All right. Well, I'm Winston House, and this is Go Fish. It's a foolproof and user-friendly solution to the problem of phishing, which doesn't require any server-side changes. So how this all got started. Back in high school, I found out what phishing is, which is creating a fake website to steal personal or financial information from an unsuspecting user. So I created a fake Facebook and very quickly took over about half of my graduating high school class's Facebook accounts. And then I got banned from Facebook. So I realized that was a horrible idea and decided to come up with a solution for it. So that's where the basic idea from Go Fish got started. And then I pursued it as a research project under Professor Stotts. So phishing, like I said, is the use of deceptive internet tactics to elicit personal and financial information from unsuspecting users. This is typically done through a fake website or a fake email. And in fact, there's over 500 million of these fake emails sent out each day, incurring over $9.3 billion in losses in the US just last year. So a big problem. There's a few proposed solutions to this. The main ones are white and blacklists. However, this is a retroactive approach, and with 12,000 new phishing URLs created each month, it's virtually impossible to accurately maintain all those lists. So the next approach is password management. However, these often require intense behavior change on behalf of the user, so they haven't gained much traction in the anti-phishing market. And then finally, there's user training. But the level of sophistication of phishing attacks is increasing, and so the effectiveness of these solutions are decreasing. And they also still put the burden on the user, and we don't want that to be the case. So our solution is a browser extension, very easy to download, and there's two main components to it. The first is a proactive phishing detection, which I've called a look-ahead login. And the second component is a password hashing. Using these two components, we're able to provide the user a foolproof solution while requiring a minimal behavior change. So in a little more depth, the proactive phishing detection is basically when a user comes to a web page, in the background we try to log into that web page using just bogus information. And a phishing website, unlike a legitimate website, doesn't have a database of your information. So if it accepts that information, you're on a phishing site, and we can flag that. The other component is a password hashing. So we provide the user a unique password for every website they visit. So that way, if you type in your password on a phishing website, what would be sent would be different than if you typed in that same password on the legitimate website. So using these two techniques, we're able to prevent phishing attacks and also common password attacks, which is where an attacker somehow manages to obtain your password to one website, and because most people use the same or similar password on other websites, they're able to access your other accounts. So this, giving you a unique password, prevents common password attacks from being effective. So we've got a quick video demonstration just to walk you through this. So here I am, I'm in my email, and it looks like I've got an email from Amazon. If we look closely, it's actually coming from Amazon.com. So this is an example of a phishing email. I'll go ahead and click the link. If I click the link, it takes me to a fake Amazon page, and GoFish instantly identifies that it's a fake website and flags that, and that's that look-ahead login. As I type in my password, I'm actually typing in the word Winston, but GoFish is doing a mapping to prevent other attacks, which I'll explain in a bit. As I leave the password field, it encrypts the word Winston, or hashes it, and that's what's sent over. On legitimate Amazon, GoFish flags it as a safe site. It wasn't able to log in. And we allow the user to turn encryption on or off, or the hashing on or off. We recommend you always keep it on, but if you do wish to turn it off, you simply click and confirm you're on the website you think you're on, so that way you're not on a phishing website. If you click yes, the hashing's turned off. Cool. So some of the main challenges, I'll just focus in on the password hashing part for sake of time. But JavaScript attacks, and I'll go into more depth in these in just a sec, but JavaScript attacks, so web-based attacks on trying to steal your password before it's sent. Salting. So we want the password to be unique for each website. So how do we go about doing that? Encoding. Different websites require that you have symbols or not have symbols, and they require certain minimum and maximum lengths. So how do we accommodate for that? Password resetting. So in order for this to be effective, users will have to reset their passwords to our hashed versions. We want this to be a very streamlined process and simple for the user. So how do we do that? And finally, roaming. So what if the user doesn't have GoFish installed? How can they still log into the accounts they need to log into? So JavaScript attacks, the big three are keyboard monitoring. So the web page, rather than looking for what's being submitted in the password field, might just be capturing the user's keystrokes and then storing that and sending that off. The next attack would be mock password fields. So GoFish is designed to do hashing only on fields which are identified in the HTML as a password field. But an attacker might have a text field there and replace all the characters the user types in with a little dot or an asterisk or something else. And then finally, focus attacks. So the user might begin typing in a password field, but then the attacker blurs that and moves them over to some hidden text field, and so the user would actually be typing in a hidden text field, not realizing they're not typing in that password field anymore. And this text field would be unprotected, and the attacker could gain their information. So to protect against that, to protect against keyboard monitoring. So first off, we're executing in a browser environment, and because we're executing in the browser, we have first access to the keystrokes. So if the user's typing inside of a password field, we capture those keystrokes and don't prevent those from hitting the web page. And instead, as you saw in that mapping, are sending in other characters, each one corresponding to a letter. So in that case, the A was corresponding to W, B for I. So that way we can map out the user's password and then do the hashing in the browser and reinsert that into the web page. For the mock password field attack, so the text attack where a dot might be placed in or an asterisk, we look at what the user's typing in, and after 2 or 3 characters see, is what the user's typing in what's actually appearing in the field. If it's not, we send the user a warning saying this website might be stealing your password, and we recommend you reset your password for that account as they've now gained a few characters, potentially, of your password. And then finally, for focus attacks, we have a certain minimum password threshold, and if you leave a password field before that threshold is met, we just send you a notification saying you're no longer typing in a password field. So obtaining the salt. When I first started on this, my idea was to just use the URL and use that as the salt for the user's password. However, I realized very quickly that was a horrible idea, just because as UNC there's multiple points of access, so multiple login points. And so having a unique URL would not guarantee you the same hashing on all those points. So rather, we decided to use the top-level domain, or rather the second-level domain, so unc.edu. And then the question was, do we use the page domain or the frame, or do we use the domain in the form? And we ended up deciding to use the page domain, so what's at the top of the website, rather than the form, because an attacker might spoof the form and say it's going to unc.edu until you click submit and then redirect it back to them. So for encoding, we want to focus on the password length, make sure it's the correct length, and how do we deal with special characters. So we're using a modified hash function. This hash function was actually developed at Stanford, and then I've expanded the key space of it just to provide a small additional layer of protection. And this function the hash is always the same length as what the user's password is. So that way, if the user types a legitimate length password, the hash will be the same length. And then additionally, so the reason I expanded on this was we're analyzing what the user's typing in. So if they type in a symbol, we make sure that hash contains symbols inside of it. So we just analyze what the user's typing in and put the appropriate things into the hash. So other challenges, password reset. So GoFish looks initially at your password manager and sees if you have any passwords already saved. If you have passwords saved on websites, it won't force the hashing on there, so that way you can still log in until you reset your passwords. And then we want to set up a password reset field. So anytime GoFish encounters a password reset form, it turns the hashing off on the first field and then turns hashing on the 2 new fields or 1 new field, depending on how it is. So that way you can type in your current password into all 3 of those fields, and you've now reset it to the hashed version. So it's very easy to do, but if you want to hold off, that's why we allow the user to turn the hashing off on websites. So they do it on their own time. So then for roaming, mobile devices is a huge thing we have to deal with. But there's a growing shift for browser extensions that are downloaded on the desktop to be automatically installed on your mobile device and on that browser. So we're relying on that. And then additionally, on our website, if you type in the URL that you're trying to log into, or simply the top-level domain or second-level domain, and what password you think you're typing in, we just run the algorithm and tell you what your actual password is. So that way you can use that to log in. So this started out as a research project, but is also becoming a business. So there's a few team members, many of whom attend UNC. Ben Clark has just joined our team. He's a senior in computer science. And we also have an advisory board consisting of Chris Evans, David Stotts, and Glenn Kaplan. So we're currently filing for software patents. We've got a few interested users as we move into beta testing later this summer, including UNC's medical school has offered to test this, and a few national organizations. We'll be working in American Underground this summer. We've got some office space there, and hopefully this fall we'll launch it to market. So this has been entered in Carolina Challenge. We were winners at the high-tech track, and this was also voted the most innovative technology among undergrads in North Carolina last year by the Triangle Technology Executive Council. So thank you for your time. I'd be happy to take any questions.
I would think that another problem would be servers that change the name sometimes. Now this computer is, and sometimes they change the URLs. Does that affect your ability to log in?
They're typically not changing their top 2 domains, and so in that case, that's not that much of an issue. But we do allow in our preferences you to cluster different top-level domains together. So for instance, amazon.co.uk and amazon.com should have the same login, but our system would treat them as different. But you can very easily cluster those together, and it will just know to use the same hash on all of those.
I was surprised to hear your awesome solution to the rules on websites, and like the fact that you can't have some links on and so forth. Did you guys ever consider sort of like maybe probing for that information, whether making attempts to register with a more secure hash, or maybe like codifying on a per domain basis what kind of rules they have, or did you just go straight on that?
This was the first idea we had, and it seemed to work, so we just stuck with that. Yeah.
Matt, do you want to ask a question?
Yeah, I was going to ask, well, I guess I'll just ask one of them. So you mentioned that you're using some random hash functions that had been developed since Stanford, you said. I was wondering what kind of level of cryptographic review that had, because,
Yeah. So. Yeah, no, we're mapping an existing hash function to that. So, yep.
Great.
Cool. Thank you.
Thank you. Okay. Next up, we have our final session on applications, and we'll start it out with a project that originally debuted here some number of years ago. I don't recall. On the on the Tar Heel Reader, and now we'll hear about an offline version by Amin. One of the few demos for which he doesn't want the network. Can you try and get projected on the...
Yeah.
Is this projector off?
Oh, it's off.
That's what the issue is.
I think so. Cool. All right. Hey, everyone. My name is Amin Sheikh, and this past semester, I worked under Dr. Bishop on a project called Offline Tar Heel Reader using HTML5 app cache. And just to give you a bit of background on Tar Heel Reader, if you're not familiar with it, TarHeelReader.com is an online library created and maintained by Dr. Bishop and several other students. And it's essentially a large collection of picture books primarily targeted towards young children with disabilities, but are also used by a lot of users, for example, who are trying to practice English or trying to learn English, and several other reasons. And my project basically focuses on creating an offline version for Tar Heel Reader where users can continue to use the website even if they're not connected to the internet. So there are several motivations behind this project. First and foremost, a lot of our users don't have constant access to the internet, especially our international users, and we wanted to provide them a means to read books even when they're not connected to the internet, because right now, when they're not able to read the books. And in addition to this, Tar Heel readers often access using mobile devices, especially tablets, iPads, and a lot of times these devices move in and out of Wi-Fi zones and not always connected to the internet. And again, we want them to be able to continue to be able to read books. And this is especially a problem in schools, which often don't have Wi-Fi at all. So before I go into how I implemented this, I just want to talk a bit about offline web applications. The phrase offline web application sounds a bit like a contradiction. Typically, when you think web application, you think you're connected to a network. You request a page from a server, which you download, and then your browser displays it. So how does this work if you're offline? How do you download these resources from servers? And you can't, but there's a workaround, and that's you download them when you're online, and then your browser caches them so that you can use them later when you are offline. Now, this is kind of the solution that is provided by HTML5 app cache, which right now is the most reliable way to create offline applications. And I'll talk a bit about that now. HTML5 app cache is essentially an interface provided by HTML5, which allows you to specify resources. When I say resources, I mean HTML files, JavaScript pages, scripts, images, or any assets that you would use in a typical web application. And you can cache these for either offline usage, if you want to increase speed in your web application, or you want to just reduce server load. In our case, we want to create an offline application, and that's our main usage. And these resources are typically listed in what's called a cache manifest file. Cache manifest file will have an app cache file extension, and you can specify this file path in an HTML element in an HTML file. And when you serve this file, you need to configure your server so that it can give the right MIME type. Here we have text/cache manifest is the MIME type for these files. And that's just basically the basic setup for using HTML5 app cache. And here's kind of a diagram which displays the process. So you have a web page which you fetch from a server. You're connected to the internet. And the web page refers to a cache manifest file, like you saw in the previous slide. And in this file, you have a certain number of resources listed. Again, HTML files, scripts, images, whatnot. And once the app cache interface sees this file and all the resources listed within, it will cache all of them. And then in subsequent requests to those resources, instead of getting them from the server, it'll get them directly from app cache. And this allows for offline browsing. You can cache other pages in your application so that you can browse it just like a normal application when you're connected to the internet. So I'm going to talk a bit about the cache manifest file. This is where most of the work happens. This is where you can really set up an application. There's three main parts to it. First, you have the cache section. This is an explicit list of resources that you want to be cached. This is where you define all your HTML files, scripts, etc. You also have what's called a network section, and this is essentially a whitelist for resources that you don't want to be cached because they require a network connection. Think server-side code, and this actually doesn't really pertain to offline applications as much. If you recall, I mentioned earlier that people use app cache just to speed up their application, and if you have certain resources that you don't want to be cached, this is the place to specify them. And last, you have the fallback section, which is fairly important. You can specify fallbacks for resources that are not accessible. If some resource, for example, is not cached, you can specify that any resource that's not cached will directly fall back to another page or another resource that you've also specified. And I'll demonstrate that in a bit. So here I have a simple cache manifest file. At the top, you have this cache manifest string that's required, and comments are specified using the pound symbol. And as you can see in the cache section, you have I'm just specifying a CSS file and a JavaScript file. If you notice, there's actually no HTML file, and the reason is when you specify in an HTML element that you're using a manifest file, that HTML file will automatically be cached, so you don't actually need to specify it, and that's why it's not there. In the network section, I just have some PHP files that require network access to use, so hence they won't be cached. And lastly, I have the fallback section. And in this example, any images in the images folder will, if they're not cached, they will automatically display offline.jpg instead. And any HTML files that are not cached will automatically display offline.html. So it's kind of like a backup if they're not directly cached. Now this is a kind of a static manifest file. It assumes that you know which resources will be used in advance, and in most web applications, it's not really the case. Consider, for example, TarHeelReader.com. This is an example of our favorites page. Each user can select specific books that they consider their favorites, and this will vary from user to user. So there's really no way for us to, in advance, specify what's being cached. And that's where the real challenge comes in. The way we really have to do is we have to dynamically generate a cache manifest file. Here's just an example using PHP of how you might do this. First, you have to specify the MIME type as a cache manifest. And I'm just echoing the important parts of the cache manifest file. And since it is a PHP file, you can programmatically compute the file paths that you need to and echo them to generate a cache manifest file. And this is typically how it's done in web applications, and it's how we did in Tar Heel Reader as well. So now I'm going to talk more about how app cache is used in TarHeelReader.com. Basically, the way we wanted to set it up is the user will have an option to enter an offline mode, and as soon as the user does this, a cache manifest file will be generated based off the user's favorited books, and all of the images, the HTML files in that book will automatically be cached in a cache manifest file. And when they enter offline mode, they'll essentially be displayed the favorites page where they can read all of these books. So just to give you a demonstration of this, here I have in this screen over here TarHeelReader.com. I will favorite some books. And then I will enter offline mode. Now I'm turning off my Wi-Fi just to show you that I'm not connected anymore. I'm going to go to google.com and it's not going to work. And when I try to access this book, it will allow me to read it like normal. This is completely offline. And yeah, I can read any of these books. And in fact, if I open up a new window and try going to the website, I've set it so that it immediately falls back to the favorites page. This is especially nice in for example, tablets where users have just saved this web page on their home screen and they don't really look at the URL and they just open it up. If they are offline, it'll go directly to their favorites page. Just kind of a nice feature. And yeah, that's essentially how it works, a completely offline application. So going forward with this project, some of the main things we need to do is we need to make it work on other browsers. The scope of this project, we only focused on Google Chrome and WebKit. We've tested it briefly on Safari, and it seems to work, but we need more testing. Another issue is one of the potential drawbacks with App Cache is that even when a connection exists, it prefers to use the resource in App Cache if it exists in App Cache. And when we make changes to our web page, they might not be, the users might not be able to see them because, for example, they don't clear their cache or something. And we need to find out a clever solution to get around that. And in general, just more testing, especially on mobile devices. Just trying to see if everything works. And yeah, thanks for listening. You guys have any questions?
Do you still write books while you're offline?
No, you can't.
You can't?
No, anything that requires a network connection.
So like when you go back online, what is it?
Yeah, if you can go back online, then you can use it as a normal
But
application.
you can't have it send it to offline?
No.
When you go back open?
No, you can't. No, there's no. It doesn't really maintain state between.
Next undergraduate research project.
I was going to ask the same thing, but you can cache user actions when you're offline and then send them later when you go back on. But
No, you can't. No. Dr. Vaughn?
Okay. So the user had to manually these favorites are books that the person reads again and again?
That they've selected as favorites.
There's a lot of work in file systems that try to determine things that are accessed or many times it's called holding. Where you automatically hold the things that are frequently accessed. So I assume that's what you're assuming here, right? That favorites are the ones people read again and again, so you can scan them.
It doesn't intelligently determine what their favorites are. It's more what they've selected as their favorites.
Your teachers will select those books that they're going to use with Sebastian. I got these for Johnny and these for Billy and these, and then I'm going to give the kid access.
So they're not going to read the book again.
So it's about, the kids will read the books over and over. You know, a kid with autism is going to read the book about ceiling fans 1,000 times, all right? You know? But, yeah, so they're favorites in that sense, but it's also a mechanism for reducing choice, right? I wanted the child to be able to self-select their reading. That's super important. I chose the book. But the teacher wanted some control over that choice. I didn't want you to read anything. You know, what do you do with history now? And you choose the history books to read. And it was also an easy place to have a subset of books.
Right. How long does that caching usually take, and are they notified that it's been done, or are they cut off? Or?
Yeah, so right now there's no notification. It does take a few seconds, especially if they've chosen a lot of books. That might be something we need to add in the future. There is actually an event, a JavaScript event that's that you can, when the caching is completed, so that we can do that.
Is there any other types of content that you think this could easily be ported to also cache? Or, I mean, it's not totally general purpose at this point, right?
I'm not sure I understand.
So yeah, I'm thinking of any website. Would it automatically work in the same? I mean, obviously, favorites doesn't make any sense, but anything.
Yeah, you can. Yeah, yeah.
The site itself.
Yeah, you have to put in that manifest, that app cache is from.
So the Amazon Kindle reader online.
That's an app cache?
Yes. Fabulous. You know, you say, I want to read this book. It imports it into your app cache, and then when you're offline, you can read the book just fine.
But it's actually back.
Yes, they actually send it back. They're, so they're one step behind.
Moderate discussion after the session. So our next talk is also on text and, in this case, natural language. And this is by And did we get the mic back on?
Oh, sorry.
Click that on. And it's,
Hello, so I'm Keithan. I'm a senior here at UNC, and I've been working with Dr. Ahalt. So I investigated authorship attribution, which is just a fancy word for deciding or determining the author of some text. And so this is done by creating a model for each of the possible authors from text files with known authorship. And these models can be generated in multiple ways, as you'll see. So a fairly simple way is just looking at word frequency. So both the test file, the file with unknown authorship, and the train file, you basically gather the word frequencies and then compare for each word in there. And so you take these differences and sum them up, and the train file that has the lowest sum with the test file, you assign the author of. But there are slightly more complicated ways where basically you can just compress the files and compare the compression rates. So the way this is done is you compress each of your train files, one per author, and then you concatenate the test file in question to each of those train files and compress each of those new files that you just created. And then you compare these new sizes. And so the idea is if someone wrote both of these files, then the test file will be able to compress very well with the train file. And the reason this works is because of entropy, specifically Shannon entropy, the entropy of data. And so this is just a measure of how few patterns are in the data. And it is a theoretical limit on the best lossless compression there is. And so when you actually perform compression, it is an approximation of the Shannon entropy. So the compression method that I used was the zip file format, and specifically the deflate method, which is a mixture of LZ77 and Huffman coding. LZ77 basically takes a fixed size window that moves across the data as you parse through it, and if it identifies a string that was seen previously in the window, instead of keeping the string, it just references back to where it last saw it in the window. So it does that first. And then Huffman coding goes through and basically changes how each of the symbols are represented. So very common symbols, such as an E, will be represented with fewer bits than something like a Q, probably. So I did this on two types of data. One was forum posts taken from a health advice forum. So it's all from doctors, telling people what's wrong with them, and emails that people were generous enough to donate to me. And so for the forum posts, the train files and test files included the same number of forum posts, whereas with the emails, I did it two ways, where there was only one email in the test file and all the other emails were in the train file, and I also did a 50-50 split, like with the forum posts. And so when we did this for word frequency, all of the forum posts got categorized to the correct author. The emails, none of them did, unfortunately. And this was for both only having one email in the test file and having a 50-50 split. It didn't make a difference how much you trained the model. For compression, all the forum posts, again, were categorized correctly. And the emails, 2 out of 6 of the authors were identically or correctly identified. But all of the errors arose from being incorrectly assigned to category 5. So when I removed the 5th author from the data set, I got another correct match. So there are a couple of reasons why the email data set didn't do as well as the forum posts. First of all, the emails are scattered on many different topics and subjects and people. And I mean, you all have written emails. You don't just write one type of email about one specific topic ever. Whereas with forum posts, if you're posting to a forum, it's pretty much all on the same exact topic. And then with author number 5 for the emails, it was formatted slightly different than the others. The others the others had lots of gaps and spacing and dividers between the emails. The formatting of email or of the author 5's emails was they were all just scrunched together with one new line between emails. And so for the other authors, they had all this blank space and all of these repeated sequences, and so they got compressed really well. But then author 5 didn't get compressed very well. And when I added these other authors onto it, I actually got a better compression than without adding the extra text, just because there were repetitions that it could work with. So compression did work a little bit better than word frequency. The emails, it wasn't quite perfect. And this does show that approximating the entropy can work for this instead of word frequency or stuff like that. And it's especially useful because looking at word frequencies only looks at words, whereas entropy is done per character. So you get words, you get word roots, you get strings of words. All of that is taken into account when doing this. And so future work that still has to be done is you can take out the most commonly used words from the word frequencies, things like the and a, things like that. Like all of the files are going to use those words a lot, and that's really going to drown out everything else. And so if you take those out, you can get more distinction between all of your files. Another thing is use different compression algorithms, such as 7-zip, gzip, many others. Specifically, current research being done in this area more or less agrees that the RAR file type works best for this. You get best results for authorship attribution when the files are compressed with RAR. Unfortunately, it's proprietary, so I can't do anything with that. And then another thing that you can do is when you identify the author of one of your test files, you can then add that to the train file and add it into your model for future tests. So that's another thing that still has to be done. Any questions?
Questions?
So how many distinct authors do you think you can distinguish between?
I mean,
1 million different authors.
I think it really depends on the data. If you're looking at a bunch of romance novelists, that's going to be hard. But if you're looking at, if the authors themselves are varied, then it probably could.
Hey, there was a question over here for you. These are all of them. I believe I can paraphrase that as just wondering the extent of your expertise with romance novels.
None, actually. That was just a genre that I thought might be fairly similar per author. I don't know.
The plots are fairly similar between them.
Are they? Okay. Okay.
Are you testing for plot as well?
No. Yes.
Something in between kind of just single word frequency and kind of entropy, character frequency, would be something like Markov chains?
Yeah, yeah. So the research into compression actually is from Markov processes, Markov chains. It is how likely are you to know the next character based on this character. So.
And it seemed to me that doing that based on words rather than characters might be the meaningful unit. So in other words, if an author were to tend to use the same phrasing over and over, maybe even a romance author, I don't know. That would be, I'm trying to think how I would even, the other question I have is how do you know how well you should be able to do, right?
I mean, all I have to go on is compare against studies that have been done on hundreds of thousands of text files. That's all I have to compare to.
Turing test for this, right? There's a world expert in knowing authorship that can just tell you, this is how well I do. You ought not be able to do better than.
Sorry.
There's got to be some human interactive thing where you get your thing in the computer we're better or worse at this type of thing.
And you maybe ask me, we each write something, and then you ask, did I write this? If I couldn't tell.
If you wrote your own thing?
Yeah. Or could I tell maybe, was this yours or mine?
Exactly. Quick fire question for you. So you said the score is essentially the compression ratio, right? Not the rate?
No, the compression rate. So you basically take the compressed file between the train file and the train plus test.
Right.
You compress those and just subtract the sizes.
Secondly, I know you want huge training for bio, but how big should your sample of your test file be to actually have some confidence in the outcome?
Again, that largely depends on the data that you're using. If all of your data is fairly similar, then you need a lot to train with. If things are already pretty separate, then you don't need that much.
Has this made you put on your tinfoil hat and scramble all your emails and synonyms randomly? Okay, you're not doing that already.
So Keith, do you want to explain the context of the original problem that we never got to?
Yeah. So you may have noticed that I don't have very much data. And we originally framed this in looking at the free text part of medical forms. So if you can read that in from multiple doctors, from multiple practices, can you perform authorship attribution to determine what practice it came from? So if you can group, so the idea is all the nurses and doctors and physicians in a practice are probably going to write their notes fairly similarly so that they're easily readable by everyone else in the practice. And so we wanted to test that. Unfortunately, it's a lot harder to get the data than just having some emails donated. So.
Jake, I was just going to ask you about your word frequencies. Did you just do the pure word frequencies, or did you try and match words and combine walk and walking accounts of those together?
No, it was just pure word frequencies.
So if you can't know how well you should do, you should at least be able to estimate how well you did, right?
Yeah,
you
yeah.
could say, how much better did I compress here than some other house? So you could say, I have no idea, maybe this one. Or I'm really sure it's this one. Would that be useful to the original purpose?
Yeah, yeah. So, I mean, you have these differences in sizes, and if you have, a definite best, but there are several other train files that are really close to that, then you're not going to be that sure. but yeah, so that is something that you could do.
Did your email have included text also from other people? Were the emails composed by the author, or did it also include?
Only by the author. So it wasn't things like reply chain back and forth, and it included all that, and yeah. No. Try to take greetings and endings and headers and all that out, and just look at the content of the email, the message.